பார்த்தீங்க அப்படின்னா மேக்னட்டிசம் அண்ட் மேக்னெட்டிக் எஃபெக்ட் ஆஃப் எலக்ட்ரிக் கரண்ட். மேக்னட்டிசம் அண்ட் மேக்னெட்டிக் எஃபெக்ட் ஆஃப் எலக்ட்ரிக் கரண்ட். மேக்னட்டிசம் அப்படின்னாவே நமக்கு தெரியும். So we know the property of the magnet, we know what is meant by magnet and how it is used in the day-to-day life. Everything we know about the magnet and magnetism and magnetic effects of electric current. So next important topic is magnetic effects of electric current. So what is the effects of magnetic effects of electric current? So what is the relation between the magnet and the electric current? Okay. So in this lesson we are going to see about the magnetism and the magnetic effects of electric current. So it's a very important lesson. Then, so introduction about the magnetic field. So magnetism. So magnet. We know that what is meant by magnet and what is the property of that magnet. So in day-to-day life it is used in a various purpose, and still it has a different and very good opportunity to do the research. So இன்னும் நிறைய நம்ம கண்டுபிடிக்க வேண்டியது இருக்கு மேக்னெட்ல. So it's a wide area to do the research in magnetism and magnetic field. And magnetism is everywhere, from tiny particles like electron to the entire universe. Everything is made up of particles. So everything has some magnetism. So the magnetism name is derived from the magnetite. Magnetite is the iron ore. It's coming from the iron ore magnetite. So the magnetite or the magnet is used for navigation purpose and magnetic therapy. It is for treatment and also used in the magic shows in the older days. Okay. In modern days, we are using the magnet in dynamos, loudspeaker, magnetic tapes, audio and video recording, mobile phones, headphones, pen drive, hard disk of laptop, refrigerator, and doorbells. Generator are the few examples of the use of magnet. Okay. In this lesson, before 1820, electricity and magnetism are the two different branches. After that, 1820, Hans Christian Ørsted discovered that when current flowing through the wire nearby the counter shows the deflection. So that was discovered by Hans Christian Ørsted. After that, the two different branches are merged into the single subject, that is electromagnetism. So electric property is a very important property. So it can flow. So using that property, we are making the train without friction between the rail and the train. So using that, we can use the property of the magnet. So it's called magnetic levitation. So magnetic மேல வந்து எந்த டச் பண்ணாம அப்படியே இருக்கு. இது வந்து ட்ரெயின்ல நம்ம யூஸ் பண்றோம். அதே மாதிரி பாத்தீங்க அப்படின்னா in this unit the basic of magnets and the properties are given in the later. So what are all the properties? So we are using the MRI scan, laptop, speaker. These are all the things nowadays we are using that, and we are going to study about the property of the things. Okay. So next we are going to see the earth magnetic field and the magnetic element. Earth magnetic field and the magnetic element. First we have to see that into the theory. After that we can study in a animation picture. So first one, geographic axis. So geographic axis is a straight line passing through the geographical poles of the earth. It is the axis of rotation of the earth. It's also known as polar axis. The straight line, this is passing through the geographical poles. Geographical poles means the north pole and the south pole. And second thing is geographic meridian. Geographic meridian at any places is a vertical plane passing through the geographic north pole to south pole. Suppose one line is passing through the north pole to south pole, that is called the geographic axis. Suppose it is a plane passing through the north pole to the south pole, that is called the geographic meridian. Next thing is geographic equator. Is a great circle on the surface of the earth in a plane perpendicular to the geographic axis. All the points on the geographic equator are equal distance from the geographic poles. So equator means that it is a center line. So definitely it has the same distance from the north pole and the south pole. Next thing is magnetic axis. So magnetic axis is a straight line passing through the magnetic poles of the earth. It is inclined geographic axis nearly at an angle of 70 degree. That is called magnetic axis. Say geographic axis, it is passing through the north pole to south pole. It is 0 degree. So magnetic axis is not a 0 degree. There's a angle between the geographic axis and magnetic axis, that is a 17 degree. Next one is magnetic meridian. Magnetic meridian at any place is vertical plane passing through the magnetic north pole and south pole of the earth. So geographic meridian மாதிரி என்ன இருக்கு அப்படின்னா magnetic meridian இருக்கு. So மேல இருக்கிற மூணுமே வந்து எர்த்தோட ஆக்சிஸ், எர்த்தோட மெரிடியன், எர்த்தோட ஈக்குவட்டார். அடுத்த மூணுமே பாத்தீங்க அப்படின்னா magnetic axis, magnetic meridian and magnetic equator. So magnetic equator is a great circle on the surface of the earth in the plane perpendicular to the magnetic axis. All the points on the magnetic equator are equal distance from the magnetic poles. Next thing is declination. This is the angle of the magnetic meridian and the geographic meridian at your place is declination. It varies from the place to place. Lines shown on the map through a place that have the same decline are called isogonic line. It's called isogonic line. Line drawn through the place have zero declination is called agonic line. Okay. Next one, dip or inclination, that is taken as a delta. The angle between the horizontal component of the earth magnetic field and the earth resultant magnetic field at a place is dip or inclination at that place. So the angle between the horizontal component of the earth magnetic field and the earth resultant magnetic field, ரெண்டு நடுவுல இருக்கிற கேப் தான் என்ன சொல்றோம், angle தான் என்ன சொல்றோம் அப்படின்னா that's a dip. It is 0 at the equator and 90 at the poles. So in that equator region it has become 0, but in a pole region it is 90 degree. Lines drawn upon the map through your places have the same dip or called isoclinic lines. The line drawn through the places that have 0 dip is known as a aclinic line. It is magnetic equator. And horizontal component of earth magnetic field is called BH. So these are all the things you are going to see that in a visual animation graphics. So don't worry about the theory. So I will show you it in the animation. Okay. So the total intensity of the earth magnetic field does not lie in the horizontal plane. Instead of it lies along the direction at an angle of dip delta to the horizontal. The component of the earth magnetic field along the horizontal at an angle delta is called horizontal component of the earth magnetic field. So you know that definitely it is a resultant. See the picture. Here B2, B and B1 is there. Suppose the magnetic induction B that will divided into two component, X component and Y component, or it is called horizontal component and vertical component. Always you can take the horizontal component as a cos theta, vertical component in a sin theta. Okay. So here, so that earth magnetic field. Now we are going to see the animation about that. So see that. In 1600, William Gilbert, who was a physician to Queen Elizabeth of England, so showed that the force acting on a suspended magnetic is not due to the influence of the pole star, but to the magnetic field which is present all over the surface of the earth, as if the earth was magnetized. Gilbert made a large spherical ball from magnetite, the poles which were situated on two sides. By placing a small magnetic compass on the magnetized sphere, the Gilbert showed that the compass took a definite direction at different points on the sphere as it does in the case of the earth. According to his view, the magnetic field on the surface of the earth can be approximately represented as if caused by a huge imaginary bar magnet in the interior of the earth, but inclined to the geographic north and south axis of the earth. The concept of terrestrial magnetism has been illustrated as shown in the figure. So it is behaving like a magnet. The north end of the imaginary magnet has south polarity, while the south end possesses the north polarity. That's why the magnetic compass are shown in the opposite direction. It is attracted in the opposite poles. So declination. It has a geographic meridian and a magnetic meridian. In order to understand the term declination, let us define two terms: geographic meridian and a magnetic meridian. Geographic meridian in a plane is a vertical plane passing through the geographic north and south poles of the earth. It's a plane. Okay, that's called geographic meridian. Magnetic meridian at any place is a vertical passing through the magnetic north and the south poles of the earth. Okay. So there is an angle between the two things. The angle between the magnetic meridian and geographic meridian at a place is known as declination or variation. That is theta. That is we are going to take as theta. In figure ABCD, the magnetic meridian and A dash, B dash, C dash, D dash represent geographic meridian at a place. So already it's shown in your book. Okay, this is a two meridian, geographic meridian and a magnetic meridian. There is a gap is there, that is taken as a theta. So the angle B dash equal to theta, that's angle of declination. The angle of declination varies from the place to place on the earth's surface. Gilbert believed that the declination at any one place was constant in time, but this belief was soon proved wrong. It's not wrong, it's not right thing. There was a several periodic variation in the value of declination for a given location. So different location has a different angle value, that is the thing. So a magnetic dipole suspend freely the center of the gravity so that it can rotate about the horizontal axis. Suppose the dipole takes up the cushion as shown in figure. The angle through which the north pole dips down with reference to horizontal called the angle of dip, it varies over Earth's surface. The places where the dip is 90 degree in north pole down and 90 degree south pole down are called the magnetic poles of the Earth, generally denoted as NM and SM. So magnetic in north pole and magnetic in south pole. So NM and SM. Along a line that called the magnetic equator, which runs somewhere near the equator, the tip is 0 in equator region. The tip is 0 because there is no angle difference. Horizontal component of the Earth magnetic field. The total intensity of the Earth magnetic field does not lie in any horizontal plane. Instead, the lies along the direction making an angle delta to the horizontal. So delta is the angle, the variation of the angle. The intensity B of the Earth magnetic field can be resolved into two rectangular components. The component in the horizontal plane is called horizontal component, that is BH, or we can simply take it as H. BH or H. The component in the vertical plane is called vertical component BV, or simply we can write B. So V or H is also okay. BV or BH also you can write. So here in geographic meridian and magnetic meridian, the tan delta equal to BV by BH, that is opposite side by hypotenuse. Cos delta equal to H by B and sin delta equal to V by B. So this is sin theta and cos theta. So suppose you divide that, you will get the R, you can square and add the two values, you will get cos square delta plus sin square delta equal to square by B square plus B square by B square. So here you can add the two value, you can get 1 cos square delta plus sin square delta equal to 1 S square plus B square by B square. B square is a common for the two terms, that's why we are taking. Or B equal to root of H square plus B square. It's a very important formula. It is used for the calculation. B is equal to root of H square plus B square. Okay. So it's a very important formula for the doing the calculation. Okay.